In today's lesson, we're going to be taking a look at the idea of a derivative. Before we talk about what a derivative is, I want to revisit our problem regarding the tangent equation. Given this curve here, this function here, let's call this f at x. If you remember, for any specific point on that curve, we had a tangent equation. And that tangent equation had a slope. And if you remember, this tangent line touched the point at exactly one spot. Let's say, for instance, that this was the point 2,5. If this was the point 2,5, the slope of this line was defined to be the limit as h goes to 0 of f at 2 plus h minus f at 2 all over h. But then the issue with that is now, okay, if I want to find the tangent at a new point, I would then have to calculate the slope a second time for a second tangent equation. I'd have to go ahead and calculate the limit as h goes to 0 of f at, and let's say this is the point 5, 6. I'd have to take the limit of 5 plus h minus f at 5 over h. And we'd have to go ahead and calculate that limit all over again. So instead of doing that, we have another option. And the other option is to do what's called the derivative. What the derivative will give us is a generalized equation for the slope of any tangent, in this case, to the function f at x at any specific point x. So it'll be a generalized slope. Once you take your derivative, you can pick any value you want. You can say I'm going to let x be 2, I can let x be 5, and I can get the slope of the tangent at that specific point without having to redo your limit relationship every time. Let's see what that looks like. So now we're going to take a look at the idea of a derivative. So like I was saying, the derivative here is going to give you a generalized form for the slope of the tangent to a specific curve at any point here. So how it's defined is exactly how we were defining it. Instead of letting x be a specific number, we're going to let x be variable and just leave it as x itself and try to generalize the process. So the derivative function f at a number a is given by the following: f prime at x. So this is the notation here. Just to point this out here, this is read as f prime at x. And this superscript with a 1 in front, they refer to that as a prime, f prime at x, which means your derivative. And it turns out that as long as the limit exists, then your derivative exists. And we'll come back to this idea of when your function is differentiable and when it is not. But now let's assume we're looking at differentiable functions, and let's proceed. So let's take a look at our first example here. I have this function f at x equals x squared. I want to go ahead and I want to calculate f prime at x. So in this situation here, we're going to go ahead and I know that by definition, f prime at x is the limit as h goes to 0 of f at x plus h minus f at x all over h. Now again, normally we would have a specific point they want us to calculate the slope of the tangent at, and we would substitute in for x. We're going to leave that x there. So when I do that here, this becomes a limit as h goes to 0. Everywhere I see an x, I change that to an x plus h, x squared over h. We're still going to go ahead and use our factoring techniques. Notice here, if I let h be 0 here, we would be an indeterminate form. So we should have some cancellation and factoring techniques we can do. Well, I can do difference of squares. So this would be the limit as h goes to 0 of x plus h minus x times x plus h plus x, whole thing divided by h. So now if I take the limit as h goes to 0 here, you'll see these x's cancel, and I'm just left with h times 2x plus h all over h. Now as h goes to 0, these non-zero terms cancel, and we're now taking the limit as h goes to 0 of 2x plus h. As h goes to 0, you can see here we have a continuous function. I can sub in that h and it's defined, and we get 2x. So that means that f prime at x equals 2x. So what this gives me is the slope at any point. So now if you want to find the slope of the tangent at 2, you would evaluate f prime at 2, which in this case will be 4. If you want the slope of the tangent at -5, you would evaluate f prime at -5, in which case you get -10. So you can see here this is a more effective way of going about calculating the slope at any given point on your curve. Let's look at another. So same idea here. We want to go ahead and calculate my f prime at x. This time again, we have a parabola. It's a little more complicated, but still applies here. So I'm going to go ahead and calculate the limit. As h goes to 0, this is going to be at f at x plus h minus f at x over h, which is going to be the limit as h goes to 0. Now, everywhere I see an x, I have to change that to an x plus h. So I'm changing that to an x plus h squared. I'm going to move this over so I have a little bit more room. So now don't forget your brackets here. I get 5 minus 4x plus 3x squared, and that entire expression divided by h. So now in this case here, I'm going to expand everything out. So we have the limit as h goes to 0 of 5 minus 4x minus 4h plus 3, and we're going to expand in the power of 2 first, so this becomes x squared plus 2xh plus h squared. Don't forget to distribute that minus sign into the trinomial. This becomes minus 5 plus 4x minus 3x squared over h, and we get the limit as h goes to 0 of 5 minus 4x minus 4h. I can distribute the 3 into the trinomial as well, in which case we get 3x squared plus 6xh plus 3h squared. And now we just got to simplify all of this and hope everything cancels off so that h in the bottom can be canceled off. So I'm going to take the limit as h goes to 0 here. Collecting out my x squareds, I have a 3x squared and a minus 3x squared, so those cancel. I also have a negative 4x and a positive 4x, so those cancel. I have a 5 and a negative 5, so those cancel. And I'm left with here 3h squared plus 6xh minus 4h, the whole thing divided by h. So now I can go ahead and factor h out of the numerator, giving me h squared plus 6x minus 4 over h. And now we're taking the limit as h goes to 0, so those will cancel off. And when that starts to happen, you know that you're doing this right. And I end up getting 8 squared plus 6x minus 4. Take the limit of this polynomial as h goes to 0, in which case we get 6x minus 4. So that means that f prime at x is going to be 6x minus 4. So therefore, if I want to calculate the slope of that polynomial at any point, I just have to use my f prime at x, sub in that point, and I can get my slope of my tangent line. So for this question here, we want to find f prime at x. We're given the function f at x is x plus 1 over x minus 1. And I mean, you can tell how computationally it's a lot to go ahead and calculate the slope at any specific point. There's a lot of work to do that, so it'd be nice to have a generalized form to calculate those slopes of those tangent lines, and we do. So we're going to go ahead and use our definition. So I'm going to take the limit as h goes to 0 of f at x plus h minus f at x over h. And now everywhere that you see an x, you're going to change that to an x plus h. And now we have the limit as h goes to 0. I'm going to have to get a common denominator here. So doing that, we're going to have x plus h plus 1 times x minus 1 minus x plus h times x plus h minus 1, and that entire expression over x minus 1 times x plus h minus 1. Take that whole thing and go about and divide that by h. So now in this case here, we're going to want to expand everything out and hope for some cancellation. On top of that, this h value is over 1. So when I multiply by the flip, you're essentially just multiplying the h right here. So this becomes the limit as h goes to 0. Again, when I expand out the top here, if you take a look, I'm first taking this x value and I'm multiplying all three of these terms by x. So this will be x squared plus xh plus x. And the second term, I'm taking the minus 1 and distributing that to all three. So this will be negative x minus h minus 1. And likewise here, let's put our brackets around this and expand this out. We're going to get x squared plus xh minus x, and then plus x plus h minus 1. And that entire expression is now over h times x minus 1 x plus h minus 1. And again, to remind you guys, I changed the division to multiplication. You multiply by the flip. So you end up getting that h value ends up popping up here. So now again, I'm hoping for some cancellation, and we should get that here. I'm going to take the limit as h goes to 0. Right away, just to save us a little bit of time, I'm noticing these x's will cancel. And I'm also noticing in the brackets here, these x's will cancel. So we end up getting here x squared plus xh minus h minus 1. Distributing the minus sign, we get minus x squared minus xh minus h plus 1 all over h x minus 1 x plus h minus 1. So when we're going ahead and doing this here, again, what you want is you know that you want those h's to cancel. So as I go through here and we're checking our algebra, these are canceling. Everything's looking good. Everything's looking good. And we end up getting here, if you notice, negative 2h over h times x minus 1 x plus h minus 1. And now because of that, I can see if I take the limit as h goes to 0, these will cancel. And you end up getting the limit as h goes to 0 of negative 2 over x minus 1 x plus h minus 1. Now I can go ahead and take the limit of the top, which is just going to be itself. It's going to be negative 2. I can take the limit of the bottom, which is just a product of two polynomials, so it's continuous. I can let that h be 0, in which case here I get x minus 1 squared. So therefore, with this problem here, we have f prime at x is going to be negative 2 over x minus 1 quantity squared. All right, let's try another. So for this question here, same idea. We want our derivative, and now they give me f at x is 1 over x squared. So we've got the limit as h goes to 0 of f at x plus h minus f at x over h, in which case we take the limit as h goes to 0 of 1 over x plus h squared minus 1 over x squared, whole thing over h, is the limit as h goes to 0. Again, we have to go ahead and get a common denominator here. We get x squared minus x plus h squared over x squared, x plus h squared, and then that entire expression divided by h. So now what we're going to do is you've got yourself a difference of squares in the numerator. So this is a limit as h goes to 0 of x minus x plus h times x plus h over x squared times x plus h squared over h. And we take the limit as h goes to 0. You'll notice as I distribute this minus sign, the x's will cancel. I get negative x times 2x plus h over, again, the same idea. This is over 1. You multiply by the flip. That's going to just push that h to the denominator of the top. And we get this. And now I take the limit as h goes to 0. You'll notice here that these h's will cancel. And now we're taking a limit as h goes to 0 of negative 2x plus h over x squared times x plus h quantity squared. As you take your limit here, you can sub in that 0. End up getting negative 2x over x to the power of 4, which becomes negative 2 over x cubed. And just as a quick reminder here, I was allowed to cancel off those x's and reduce them because this function does not exist when x is not equal to 0 in general. So therefore, it's fine to go ahead and do that. So in this question here, your derivative, f prime at x, is going to be negative 2 over x cubed. Okay, that concludes our lesson on derivatives from first principles. Again, you can see here now it is a bit more work to get there, but you do have a method of calculating the generalized derivative, so you don't have to actually apply it for every single x value. Once you have your f prime at x, now you know the slope of the tangent equation at any point on that particular graph. All right, so please study these examples, study these techniques. We've been using them quite a lot here, and they starting to become hopefully a bit easier to follow along. But redo the questions, try to follow along with me, see if you can do these on your own. Thank you.